Okay, so here's a little project for you guys to try at home. The sun just flared again. Want to detect space weather from home? Hit subscribe. This is a real deal solar flare. You can see it in action right here. The sun is just throwing its tantrum once again. This time over here on the left-hand side of the sun, there's a big old solar flare. Now obviously we have satellites that are capable of seeing this. We even have spacecraft out there like the Solar Dynamics Observatory that takes pictures of our sun every 12 seconds. But what if you wanted to make your own solar flare detector? Could you do that? And more importantly, would it actually work? What you're going to need is some sort of a compass. Anything that has a needle that can spin freely. Now, any normal compass will work just fine, but I prefer these pocket ones because they have a nice little cover and they are not as affected by vibrations. In addition to that, you're even going to need some aluminum foil and perhaps a box that this whole thing could go in. If you were looking to construct something, I'm not really going to do that today, because the point of this experiment is not really to contain it or to keep it safe. The whole point of this experiment is to get the maximum amount of magnetic field lines from the sun into your device, which will then affect your compass. Let's start off with the simple version. So what you're going to do is you're going to take your compass and you're going to wrap the entire compass in tin foil. Make sure you don't leave any gaps between the foil. And then the only part of your compass that's not covered in foil is the top where the needle moves up and down. Leave that exposed. Why did I tell you to leave that part exposed? Well, if the compass works properly, then the needle will move slightly. If it's covered all the way around, it's not going to be able to move. Alright, so let's see how this works. I wrapped my compass in foil completely. The only part that's not wrapped is the actual area where the needle moves. And we've got our compass sitting here. We're going to set our compass down somewhere where it's not going to be disturbed. It's very important that you don't put this anywhere near any other magnets. Don't put it next to your television, speakers, wires, anything like that. The goal is to get as clean a reading as possible. So the first thing we need to do now is calibrate our compass. So you go in to take your compass, and you go in to move it around until the red end of the arrow is pointing north. That means that it is calibrated. Next, we need to figure out roughly where the sun is. I know it sounds obvious, but when you're actually doing this, it can be difficult because a lot of the times the sun is blocked by clouds. But if you look hard enough, you should be able to find where the sun is shining through. Once you found where the sun is, put your compass down somewhere nearby, and you're just going to wait. The best time of day to do this is going to be in the morning, before the sun gets too high up in the sky. And the same thing goes for sunset. You want to do this when the sun is low on the horizon, because that means the light from the sun is going to pass through more of Earth's atmosphere, which means that the geomagnetic storm will be stronger. And during a geomagnetic storm, there will be disturbances in the Earth's magnetosphere, which means that the magnetic fields that we have here on Earth will be slightly altered. That's all we're trying to detect with this device. So you're just going to take your compass and you're going to watch it. Is it moving at all? That's what I did. I waited outside with my compass, and after about an hour, I noticed that the compass was moving very slightly. It wasn't moving enough to be random, but it also wasn't moving enough to be really noticeable. But when you really look at it closely, you can see that it's moving in response to the sun. As soon as the sun comes up above the horizon, you can see the compass starts moving very slightly. And as the sun passes higher and higher in the sky, the compass eventually stops moving altogether. That's probably because the sun is so high in the sky now that the light is passing through very little of Earth's atmosphere. Remember, the atmosphere thins out the higher you go. And the point of this experiment is to have as much atmosphere between the sun and our compass as possible. After the sun passes directly overhead, I took my compass back outside with me. And sure enough, as the sun began to dip lower and lower in the sky, the compass began to turn slightly. What you might have noticed about this compass is that it doesn't turn all the way. It only turns about 2 degrees. 2 degrees doesn't sound like a lot, but when you're talking about the Earth's magnetic field, that is a lot. Remember, the Earth's magnetic field is what protects us from a lot of the harmful radiation from outer space. Without it, we would be bombarded with cosmic rays all the time. And trust me, you don't want to be bombarded with cosmic rays all the time. So why does this happen? Why does the Earth's magnetic field get messed with like this? Well, it's because the sun is throwing tantrums. Obviously, we call them solar flares. But it's basically the sun having a massive magnetic disturbance that extends out into interplanetary space. Those magnetic field lines come crashing down on the Earth. And since we have our own magnetic field here, it causes a disturbance in our own magnetic field lines. And that disturbance is what messes with our compasses. It's a really cool phenomenon, and it shows just how powerful the sun is. Even though the sun is 150 million kilometers away, it can still mess with your Wi-Fi. Alright, so now that you know how to build a simple solar flare detector, it's time to step it up a notch. Because what if I told you that you could make a solar flare detector without even having to leave your house? Here's a little riddle for you guys to ponder. I come from 150 million kilometers away, but I still mess with your Wi-Fi. What am I? So the sun is 150 million kilometers away. That's how far away the sun is from the Earth. So whatever is messing with your Wi-Fi must also be 150 million kilometers away. It must be the sun. But the sun doesn't mess with your Wi-Fi, so what else could it be? Well, it would have to be something coming from the sun. We know that solar flares are magnetic disturbances, and one of the symptoms of a solar flare is auroras. Aurora is caused by charged particles from the sun entering our atmosphere and interacting with the gases in our atmosphere. Aurora are fun to watch, but they also mess with your electronics. If you live in a city, you probably won't notice it. But if you live out in the country, you probably have had some strange things happen to your electronics during a solar flare. What I'm saying is there is such a thing as a solar EMP. It's extremely rare, and usually it doesn't cause widespread blackouts. But theoretically, if a solar flare was really, really big, it could throw the entire planet into darkness for days. Now that is extremely unlikely to happen, but it's not impossible. That's why it's important that we continue to monitor the sun and take precautions. So what do you think? Do you want to build one of these devices? Let me know down in the comments. And if you like this video, be sure to hit subscribe because we do this kind of stuff all the time. That's pretty much it for this video. I hope you enjoyed it. If you did, be sure to hit subscribe. And I want to give a huge shout out to all of my supporters who helped make this video possible. Be sure to check out my social media and my website. That's pretty much it for this video. I hope you enjoyed it. If you did, be sure to hit subscribe. I'll see you next time.